Yeah, so before I start properly, I'm Miles Berry. I work at the University of Roehampton. I've been there for like 12 years or something now, which is a crazy long time to be in one job. But I enjoy it really very, very much. I work on our secondary teacher training programs, which is great fun. So the people I'm training are becoming secondary, like middle school, high school computing teachers. But they let me do other interesting things as well. So I was part of this, I am part of this AI for K-12 group. I served on CSTA's board for 4 years. I still serve on the board of Computing at Schools, which is like CSTA's little sister association here in the UK, and get up to all sorts of mischief, really. Before that, 18 years across 4 different schools, most of the time as an ICT coordinator back in the day before we had computing as a subject. Before that, I actually studied mathematics at university. So this data science and specialized in the statistics bits of that. So the data science thing is sort of a return to my roots, which is good for me. There are other people who've arrived whilst I've just been chatting like that. Okay, so we're at 7:50 my time. Don't know what it is for you now. So I'm going to start because I've got loads and loads of slides here. I will try and keep an eye on the chat from time to time. So feel free to just post questions in there, which will relieve the monotony of me just going through one slide after another. These slides are all live and interactive in a binder version of this Jupyter Notebook, which lets you edit the code there in place. Google Colab won't host slide versions of Jupyter Notebooks, but it will host the original Jupyter Notebook itself. So there's a sort of notebook style version of this presentation over in Colab, which is very reliable. And it should also work in Binder. Binder tops out at sort of like 100 concurrent users to any one notebook. Judging by the numbers here, we're not quite at that number yet. But you never know, the evening is yet young. Right, on with the show then. So teaching data science. The premise is that computer science education works really well when we find some motivating contexts for teaching that. This learner-centered design thing, find the things which your pupils, your students are interested in, and bring the computer science into those particular contexts. So we have the obvious ones, things like making animations, telling stories, making computer games. That's so motivating. The lovely robotic stuff. I love the sort of digital art thing, composing music using algorithms, all of that. Absolutely brilliant. Keep doing that, please. But I think statistics, working with data, is also a really motivating context for teaching programming. So using data science as an interesting, exciting context. It works the other way around as well. Data is such an important part of all of our lives, of your students' lives these days. Many of them are going to get jobs working either directly in data science or on the peripheries of data science. And this is going to be very useful for them. But all of them are going to find themselves living in a world which is increasingly dominated by big data. And so some understanding of that, some understanding of the tools that are involved and what they can do, of the privacy and ethical issues here, ought to be part of every child's educational entitlement, I would argue. As part of the panel that designed England's computing curriculum, the national curriculum for computing, and when we were framing that, we said there are 3 elements to this subject. The foundations of it, the hardcore computer science, the programming, the algorithms, and so on. The applications of that, still getting useful things done with computers, making videos, making presentations, word processing. We didn't throw out that particular baby with the bathwater, but also the implications, what I'd term digital literacy, of thinking through how this affects me as a person and us as a society. That foundations, applications, implications model, I think, lends itself to also conceptualizing what we mean by a data science curriculum, the probability and the statistics that lies at the heart of this. Yes, at a more advanced level, you might throw in calculus and linear algebra and so on, but let's just stick with the basics there, probability and statistics. Also, using software, writing code, getting useful things done with data, presenting an analysis, communicating that to an audience. And the ethical implication side of this. And forgive me if I sort of go back to question everything and trust no one when it comes to that. And I want to spend the next, 45 minutes or so chatting about those 3 particular aspects. Let's have a look first then. Before we do that, Lots of other people have done some really good work in terms of curriculum design around data science. CSTA's lovely set of standards includes that. I'm not going to read through the bullets on the slide there, but you can reference that yourselves. You've also got that at 14 to 16 and 16 to 18-year-olds, an increasingly sophisticated model of progression through data science in the context of computing education. It's good work, it really is. A really interesting paper from colleagues over in Germany about this processes and competencies model for teaching data science. They've gone back, and this is very good theoretical framework for how we might think of that. You know, the particular processes: gathering, modeling, cleansing, implementing and optimizing, analyzing, visualizing, interpreting the data. This is the bit I get excited about. Sharing, archiving, and wait for it, erasing the data. Really interesting ethical aspects to that. And then this sort of area of competences, the data and information, data storage and access, that more sort of CS bit, the analysis itself, the ethics and the protection. Their grid includes the detail in there. I'll refer you to their work. Really nice international curriculum for introductory data science, which, like I do, starts with a list of foundational ideas. Their foundations are actually much closer to my applications than than anything else. So they've got data science and me, you know, bringing this personal, making this make sense in the context of the individual. And then they look at single features, pairs of features, relationship between them, multiple features, graphical displays and tables, sorry about the typo there, data handling pipeline, and avoiding being misled by the data. Some really nice sort of implication stuff. And then they go into particular areas of application. And again, some nice work there in thinking about the sorts of things. And their recommendation is you don't sort of cover the whole list, you pick some interesting topics from that. So other people, as I say, have done good work in this area. I think we can make this a very practical introduction and use tools with which they're familiar, tools which are readily accessible to them. So yeah, start with Excel or start with Google Sheets. Personally, a fan of the Google stuff. There's a lovely free, well, it's free if you use the public version, data visualization tool called Tableau that I'm using with some of my digital media students at Roehampton. Seen some really nice work being done in a tool called Orange. But if we're using Python as our programming language of choice in high school, maybe even in middle school, then Python has some really nice data analysis, data visualization libraries. So make use of those, build on their coding skills to add in this motivating context of data science and to help them make sense of some of these ideas in probability and statistics. Really good Python data analysis libraries called Pandas, and lovely visualization tools. I'm a fan of the Seaborn graphics package. High-end stuff moves into R as, you know, the data scientist programming language of choice, but I think that's too early to move to that if they're still at middle school and high school. Plenty of room left in Python. Need some sort of editor. I'm using Jupyter because of that sort of dialogue with the interpreter, being able to ask it a question and get the response back. I think it's a really nice tool for that sort of mathematical, exploratory type analysis. Other tools, of course, are available. Personally, becoming a fan of Visual Studio Code. You can host Jupyter notebooks in all sorts of places. Google Colab is great for this. I should have deleted this. Azure Notebooks was around until like yesterday. I think you can still host a Jupyter notebook up in Microsoft's Azure cloud, but you've got to pay for it now, and it's become a lot more complicated. And Binder is, you know, purpose-built hosting of Jupyter notebooks, which is what I'm using for the first version of these slides. As it says, other tools are definitely available. So let's think about that foundations layer. And I think you've got some really nice ideas in probability, ideas in statistics that let them write useful or at least interesting code. Let's have a look at some examples of this. I'm just going to bring in some of the standard libraries. I've got matplotlib as my plot library for this. I've got random functions. Let's just run that code and then move on to the next thing. So what we're going to do here, I've written a couple of functions. First one rolls a dice. It defaults to one dice with 6 sides, and then returns the score. It depends how many dice we're going to roll, and then how many times we're going to do that. And again, we're going to call the function here, roll 2 6-sided dice 100 times, and let's have a look at the last 20 of those rolls. So we got, yeah, 7s coming up a lot here. I've got the number 2. Didn't see any 12s in those last 20s, no 1s in those last 20s, unsurprisingly. So we've got our data, we've generated a set of data here. We can find out how many times each of those came up. So I'm interested here, how many times did the number 7 come up in my 100 rolls of a pair of 6-sided dice? So all I'm doing is counting the number of 7s out of that list of data divided by how many things we have there. I get 16% of the time was the number 7. Is that more or less than what you'd expect? If we did it again, would our answers be similar to that or rather different from that? What about all of those numbers? Let's get all of those numbers. I'm going to look from 1 up to, but not including 13 here. I'm just creating a table here. And for each of those, I'm just going to add in the relative frequency of each of those numbers in that range. Let's have a look at that. So no 1s, 3% of them were 2s, 3% of them 3s, and so on. So we've got that. We could, of course, get a bar chart out of that with just one line of code. This is so much nicer than Excel because we only have to write code here and we get the thing out of it. Let's have a look at that as a bar chart. Or not. There we go. Okay, it was a scary moment. I was just thinking whether to draw the bar chart or not. So there we go. We've got a distribution of the data here. Some things come up a lot more than others. This is the sort of thing you'd expect if you're rolling a couple of dice. But we're going into that probability theory rather than rolling the dice in the classroom. We've got Excel to roll the dice. Sorry, we've got Python to roll the dice for us. So your introductory statistics course is going to include your measures of central tendency, the mean, the median, the mode, the median, some measures of spread, the range, and then at a slightly higher level, this idea of standard deviation. We can get, of course, Python to calculate all of those, but it's much more fun to get your pupils, students, creating their own functions to compute each of these statistics. Let's have a look at those. So how would you go about programming Python to find the mean of a set of data? Well, the mean is what you get if you add up all of the numbers, divide by the number you've got there. So my function here on the screen here, start with a total of 0, start with a count of 0 for everything in the data, add it into the total, increment the count, and at the end of that, return the total divided by the count. It should be a reasonably robust way of doing it. For the data we had earlier, we get a mean of 6.97 out of it, which is pretty close to what you would theoretically expect of this. With 1,000 rolls, would that be very different? There are other ways of calculating the mean. So you could just create the sum of the data. You don't have to do that iterating over the list, which is a fairly standard technique for what we have in our sort of 16 plus computing qualifications. Oops, sorry, wrong direction. Next slide, please. Okay, we could just add it up. Python has a function to do that. We could calculate the length of the list, divide one by the other. If you want to show off with your functional programming skills, then we could do some sort of clever higher order function implementation of this. And of course, Python has a built-in function to work out the mean. From statistics, import mean, job done. I have students who think that's the best way to write code. They may be right, of course. Okay, the mode of the data, I think that's that to my mind is a harder question to do because we've got to figure out which of these numbers came up most often. You remember I've already got my frequency table. I've already done my frequency, relative frequency counting for this. So I can do a similar sort of thing. Let's create the frequency table on the fly here. I'm going to use a dictionary as a data structure for this. For every single data item, I'm going to see if it's in the list of keys already in my frequent dictionary. If it's not, add it in as a key to the dictionary and set its value as 1. If it is already in my dictionary, then just increment the value of the data for that by 1. And then return the frequency table. Let's have a look what that looks like. So we got 16 7s, which is pretty much what we found earlier. We got the next thing was a 5 that came up 14 times. Again, it would be helpful if we have this in order. Dictionaries don't come with a natural ordering in Python. So let's have a look at that. 3 2s, 3 3s. It's very much like my relative frequency scores earlier, done in a slightly different way. Okay, we may as well plot a bar chart of that as well. So this is going to be a very similar picture to what we got earlier on. This time, though, I'm not starting at 1. I'm starting with the data itself and plotting each of those points. It's exactly the same shape as we got earlier. Okay, the mode then is simply which of those came up with the highest frequency. It should return as 7. To find that, once I've got my frequency table, I can just go through and have a look for which of those has the highest value. It has the highest value. So set max up to 0 at the start of this, go through the frequency table. Every time it's bigger than that max, update the max to that frequency, and then change the mode to what we found there. And we should get the mode out from our data, 7, just as you saw on the chart. So we've written a function to do the mean, we've written a function to do the mode. Finding the median, which is the middle thing if you've got an ordered list of data. Well, we've got to put the list of data into order. I suspect there are faster ways of doing this, but I think they're way beyond the sort of level I'd expect of middle school coders. So firstly, getting the list into order, Python has a built-in function to do that, but I can write my own sorting algorithms for this, my own sorting functions for this. And okay, we might start with bubble sort or insertion sort, but I reckon quicksort is the easiest function to code once you get into functional programming. So all I'm doing here is take it, if I've got nothing in the list, then there's nothing to return. If, on the other hand, I have got something in the list, I take the first item in the list and then split the list into 2. Everything that's lower than that first item at the front, everything that's bigger than that first item at the end, and then keep doing that recursively. So what we've got here is quicksort of the lower half plus that pivot item plus the quicksort of the upper half. And that should give me a sorted list. Really nice implementation of quicksort without worrying about pointers and array indexing and so on, just by working with higher order functions and lists, or just working with functions and lists, recursive functions and lists. And then the median, I just take the middle thing on that. So the median of my list of 100 dice scores, surprise, surprise, was 7. Again, the range, simply the maximum take away the minimum. We can find that by, again, iterating over the list, keep updating the minimum and maximum, standard algorithmic approach to this, and we should get the answer 10. The standard deviation we will cover later in the math curriculum. What you're looking at there is 2 alternative presentations of that. The usual way of teaching it is to say that the standard deviation is the average of the squared deviation from the mean, and then take the square root of that. So the square root of the mean squared deviation. I've got my function to do that here. That's equivalent to the mean of the squares minus the square of the means. Now, you might have your own personal preference for that. You should have set up the poll beforehand. Let's run that, see what we get. It's pretty much exactly the same answer to lots and lots of decimal places with both methods. So you have a personal preference for one or the other. Okay, so you've got all of that introductory statistics stuff, which is terribly dry when your colleagues over in math are teaching it, that we can make far, far more interesting by bringing it over here into Python coding, writing some functions ourselves to calculate all of those statistics from the data. In order to do that, they've got to have a really good understanding of what those statistical ideas are, as well as a certain amount of coding skills. But I think, again, motivating context for teaching coding, writing your own function to work out the mean. Okay, let's move on to the really fun stuff, which is this idea of the applications of our statistics and probability to working with big data sets, to working with data and finding some patterns and making some conclusions for that. And there's loads and loads of publicly accessible data sets that I think young people are going to get really quite interested in. And what I'm going to use is the weather data since 1948 for Heathrow Airport. Heathrow airports used to be the sorts of places we travelled through to get from one country to another or get around a big country. Amazing places. Some of you may be old enough to remember travelling via airports. Heathrow is the one which we have in London, and we started about 1948, where airports really do need to know fairly accurately what the weather is, and smart airports will keep a record of that over time. And we've got access to that historical weather data from Heathrow. If you don't want to do that, then start keeping weather records yourself. This is my wife's coloured in version of the temperatures in our hometown here over 2017. Colour coding this for really cold days and really warm days in the summer. I live in a very temperate sort of climate here, and lovely, lovely ways of getting young people to start doing that weather recording before they start looking at publicly accessible sets of weather weather. The folks at the New Zealand Census at School project have this really nice sort of cyclic approach to asking and answering questions using data. And I think this is, a really nice way of doing it. There are plenty of other similar sort of cyclic approaches here, but start, they say, not with the data itself and what you can do, all the statistical tools and techniques and the code, but start with the questions that you'd like answered. So, have I got questions that are interesting to answer in the context of this weather data? So, one of my questions is the winter wetter than the summer? So it was a really rainy day here today, and I'm inclined towards the position that the winter it rains a lot and the summer it's kind of sunny and doesn't rain very much. What does the historical weather data tell me about that? My other one is, we've got these sort of shoulder seasons, the spring, the fall. Which of those actually is the warmer? Is it warmer in the spring? Is it warmer in the fall? What do you think? What is it like where you are? And then, of course, the big question of all, has the climate changed? Are we heading towards global climate catastrophe? What does the data actually say about that? So, fairly trivial ones for the first two, and kind of a big question for the last one there. So let's have a go at this, using these pandas and seaborn libraries in Python to do most of the heavy lifting for this. I'm not going to be using my home-built mean, median, mode functions, so that you could do that. Okay, so we're going to import some standard libraries here. We're going to nick the data off the interwebs. I'm going to the Met Office website and downloading the Heathrow data. If you're interested in doing this in a US context, you've got really good data from NOAA. So your approach would be slightly different, but it's going to be the same sort of overall structure to this sort of thing. And there we go, 46,000 records by the looks of it. Next slide, please. So the next bit is the bit where, if you want to just step away from the screen for a moment, you don't get to see the sausages being made here. The next bit is really kind of unpleasant. And this is where so much of the horrible work of a data scientist takes place, is this sort of, fiddly, difficult, unpleasant code of parsing the data from the format you download it from off the web into a format where you can do some meaningful, useful analysis with it, getting rid of all of the little asterisks and interpreting the NAs in a way which makes sense. So yeah, ignore all of this, please. Look away now. And then let's just have a look at the last three rows of our table there. We've got the weather at Heathrow, averaged over the whole of October, November, December. Let me just go through the column headings here. That's the year, that's the month number, that's the average monthly minimum. So take the daily minimum temperatures, average that over the whole month, and you get the monthly minimum temperature. Do the same thing for the maximum temperatures day by day. And then I can get the average temperature for the month, which is just halfway in between those two. It's nothing sophisticated there. This is the number of days of frost in the month where the temperature dropped below 32 Fahrenheit, 0 Celsius. Oh yeah, these are obviously Celsius temperatures. This is the rainfall in millimeters, and this is the hours of sunshine. And just by looking at those numbers, you could start describing what that month was like. Well, October was sunnier than December. Shock horror. October was a lot rainier than either November or December, wasn't it? And of course, December was quite a lot colder than the two preceding months. So, you can write your sort of portrait of or biography of the month's weather there. I'm going to do some comparisons between seasons and decades later. So I'm dealing with that now rather than later on. So just adding in a couple of columns at the end there for the season and the decade. Okay, so all of that stuff I did in the first bit about, the theoretical probability and statistics stuff, we can just, call one single command, and pandas inside Python will do that analysis for us. It says we've got 876 occasions when we've recorded a month number. So we've got slightly less for that for frost. We didn't start recording sunshine at Heathrow until a little later on. So bear that in mind. We can work out the mean, we can work out the standard deviation. We've also got the minimum, the maximum, the halfway point, my median scores, and these are the lower quartile and upper quartile. So that describes the data set as a whole there. Okay, so once you've got the data there in a useful format, Pandas calls this a data frame, you can start asking interesting questions. Now, thinking back to lockdown 1, or lockdown 1.0 as we call it in England, May, when we were all sort of made to be at home and not allowed out apart from 1 hour a day, was a glorious month. You know, it would have been lovely to get out to the seaside and the countryside. We're allowed out for 1 hour a day of exercise, or felt at times almost compulsory exercise. It was an incredibly sunny month, you know, day after day of like wall-to-wall sunshine. We didn't get very much rain at all. I'm curious of how unusual was that. So let's have a look at my table there, and we find out that May 2020 was the fourth least rainy month on record there. That we, you know, in terms of the amount of rainfall, 2 millimeters across the whole month, hardly anything. And that, since Heathrow started keeping weather records, that's fourth on our league table there. And look at the sunshine hours during May. I could do that. We could do the analysis by sunshine as well. So 308 hours of sunshine in May 2020. What a glorious month to not be allowed out of the house. We can do much more complicated queries. So let's have a look at all the months where the minimum was below 0 Celsius, 32 Fahrenheit, or where there were more than 15 days of frost, and we get the top 10 of those sorted by the minimum temperature, the monthly minimum temperature. And look how cold these were. You know, this is the average temperature for 3 of those was below freezing point. Interesting when you look at it. Look how this 1960s, 50s, 80s, 70s, 60s, 80s. This is the only one in that top 10 from the 2010s. Older months seem to have been colder than more recent months. We might come back to that in a little while. Okay, we can get the average maximum temperature for each month of the year. So what's the overall annual pattern out of this? And gosh, look, July seems to be a warm month, whereas January, cold month. Shock horror. And we can get that, of course, plotted as a chart. I'm not going to run the code there. So you get that visualization of that. Okay, so that's just working with the data. What does this weather data look like? I started with a couple of questions. Let's have a look back at those now. So is winter wetter than the summer? And hopefully your students would have some strategy. How could I do this? Let's work out the average rainfall for all of the winter months. Let's work out the average rainfall for all of the summer months. Is there going to be a difference in those? Which would you expect to be higher? And a similar sort of strategy, I reckon, when it comes to is spring hotter than the fall? Let's have a look at what we've got there. So it's a line of code. It's okay, a moderately complicated line of code, but it kind of makes sense. I'm grouping this by season. I'm working out the mean for these columns. I'm forgetting about the month number because it doesn't really make sense to take the average of the month number, and I'm rounding to a couple of decimal places. So we get average temperatures, numbers of days of frost, and summer was 0, okay, and the average rainfall. Isn't that amazing? Average rainfall for all of those winter months since 1948, 50.27 millimeters. Average rainfall for all of those summer months, 50.26 millimeters. Hardly anything in it. To my mind, that's counterintuitive. I think that's a moderately interesting statistic. We can draw some charts about this. Again, a couple of lines of code, and we get 4 histograms plotted to show the distribution in the temperatures there. And you can see at a glance, oh, fall. Wow, we've got some really wet months during the fall. Spring, much more sort of compact distribution. Summer, okay, generally it was fairly dry here compared to winter. You've got some really wet months in the winter, but on the whole, can you actually tell the difference by looking at it as the histogram like that? Doing a box whisker plot, here is my winter, here's my summer plot. I'm seeing, oh my gosh, look, that median line, pretty much bang on, isn't it? Yes, summer, maybe a bigger distribution between that minimum and maximum, there's not much in it, in fact, between my lower quartile and my upper quartile. There's narrative that we could write about this. So we found a difference, 0.01 of a millimetre averaged over all of those months since 1948. We can ask, is that the sort of thing which is unusual? Would a difference that big come up by random chance? Or is that the sort of thing which suggests one season is actually wetter than the other? And we can run the t-test, and again, lots of theory behind this, and you find out that no, that is an entirely insignificant result. There's nothing in it from a statistician's point of view between rain in the winter and rain in the summer. I find that surprising. Okay, let's do the same thing for temperature. Again, looking at my box whisker plot for this, I'm interested in the I'm interested in the spring and fall temperatures now, aren't I? And look, fall way, way warmer than the spring. I'm surprised by that. I tend to think of the spring as, that warm, sunny season, but actually fall is where most of the warm temperatures lie there. And again, we can do our t-test. Is that a statistically significant? And yes, that's a hugely significant finding, that autumn is significantly warmer than the fall. I tell my students not to use the word significantly unless there's a good reason. We might be interested in whether these things have any relationship with one another. We looked at rainfall, we looked at temperature. Is there a sense in which rainier months are colder? Is there a sense in which warmer months tend to have less rain? Is there any distribution there? So I can do my scatter plot for each of these months, plotting both the rainfall and the temperature numbers. And it looks a bit of a mess, really. I can't see any sort of general pattern through that. You do have a sort of banding here. So, green, the summer months are up at the top here. Blue, my winter months are down the bottom of this. And then there feels as though fall months are slightly higher on the whole than those orange months of the spring. So, those of you who've got a background in machine learning or have done any work in machine learning are thinking, oh, this looks like the iris classification problem. If you tell me the rainfall and the temperature, I can do a pretty good model here about what season of the year that data is from, at least as far as Heathrow is concerned. So you've got an interesting sort of, categorization, clustering thing going on here. We could do a similar thing this time looking at sunshine and temperature. And here I think there is a pretty clear trend line through. Okay, it's not a perfect fit, but you're generally seeing that months in which there was more sunshine seem to have higher average temperatures. That, again, shouldn't come as much of a surprise to you. And again, the banding that we saw, that sort of cluster analysis that we saw in the previous graph, I think is even clearer now. If you tell me the amount of sunshine and the temperature, I can do a pretty good model here, I would think, or my machine learning systems can do a pretty good model here as to what season of the year that measurement was taken from. Okay. So the big question, does this tell us anything about climate change? We've got records going back to 1948. That's like 70 odd years worth of data, month by month, in the way it's presented here. Is there any sort of overall trend with that? Well, let's do a line plot, time series plot. I'm looking at the temperature against the end of the month number here. It seems really sort of up and down, doesn't it? That isn't a surprise. We saw earlier that the summer months are warmer than the winter months, Northern Hemisphere sort of thing, isn't it? You would expect that annual variation in temperatures. What happens? Is there a way of smoothing that out from the data so we get to see the overall trend rather than the noise because of this annual variation in temperatures month on month? Next slide, please. There it comes. Okay, so this is just taking the average temperature for each year of my data set rather than each individual month's data. That's kind of hard to see, I think. There seems to be some sort of overall upward sloping line here, but there's still, there are warm years, there are cold years. 2010 seemed to be quite a cold year. 2020, that looks like a warm year overall. That one, 2014 at a guess, looks like a warm year. These were a bit colder. It's really kind of hard to tell just by looking at that up-down line there, as it says on the slide here. Seems to be sloping up a bit hard to see. Any other way to visualize this? This I love. So this is using Seaborn. This is using this heat map plot in Seaborn. So this is taking exactly the same data, those annual average temperatures, the average temperature for each year. And instead of plotting it vertically on that scale, colouring it in on a blue is cold, red is hot scale. And so you see immediately here, really powerful visualization of this. Look, all of those warm years are recent years. Okay, there were some back then, but generally that sort of last third, last 2/5 of the plot is a lot warmer colours than the first 3/5 of the plot there. So very, very impressive visualization of this. This is the warming stripes visualization, which is available in a range of quality merchandise. If you would like that on your flip-flops, then there is a link in the slide deck for you to order one. I've got a t-shirt. I should have worn the t-shirt for today. You remember these things just after the event, don't you? Okay, so that's looking at the annual trend there. You remember I went to the trouble of popping in all of those decade numbers. We can do the analysis decade by decade if we want, but there's a problem there in that it started in 1948. We're only at the beginning of 2021 now. So I've only got a year and a bit's worth of data from the 1940s. I've only got 12 months of data from the 2020s. So these last 2 points aren't terribly helpful. Really want to filter those out from my analysis. Next slide, please. Okay, and then when you plot it like this is the average temperature decade by decade since 1950. I think we're fairly persuaded that there's an overall upward sloping trend there. We could do something about this. We really could. There are other ways of doing this. This idea of the rolling average. Why just do arbitrary decade by decade? Why not take the average of the previous 5 years? So what I'm doing here is creating a rolling average of the previous 60 months data and plotting that as a line plot. And yes, the warming stripes is a powerful way of communicating the message, but I think it's very, very hard to find a visualization of temperatures which is clearer than this one. So what do we have here? That up until 1990, that 5-year rolling average never got above 11 degrees Celsius at Heathrow. Since 1990, that 5-year rolling average has never dipped below 11 degrees. We should do something about that. We really should. Okay, so, persuasive case made from the data. And I think inside the capabilities of, top-end middle schoolers, certainly high school students who've got some Python skills behind them, who've got some background, or at least are familiar with the ideas in the statistics. Okay, let's move on then to think through the implications of some of this. Now, I presented this as foundations, the probability of the statistics, the applications, the doing the data analysis, and now moving on to the implications. I don't think that's necessarily the best way to teach this. It's well worth integrating those 3 dimensions of the subject. And okay, not everybody you're teaching is going to go and get a job in data science, needs to know how to use pandas. They're all going to be affected by data. So yeah, I think it's worth teaching all 3 bits of this, but the really important bit is this ethics side of this. And, we've got frameworks here in the UK. We have this notion of schools must promote fundamental British values. And I bet you're wondering, what are these fundamental British values? Is it like cricket and tea and warm beer? Well, not according to our government. Our government say the fundamental British values are democracy, the rule of law, individual liberty, mutual respect and tolerance of those with different faiths and beliefs. I bet you're wondering what's fundamentally British about those, and you would be right. You might also be wondering why our politicians forgot to mention honesty or integrity on this list of British values. Who knows? Okay, so we've got, there's a remit in terms of the British English school curriculum to establish some sort of values education. I think the same is true, though, globally. There are ethical standards. ACM, which sits above CSTA, has one of our key sponsors, has this code of ethics. And I think this is worth teaching in computing lessons or computer science lessons. It's not just about the code. It is about ethical use of technology. And it's a good list. It really is a very good list. You might add your own things into that. But these principles are ones which we should be covering in our lessons. And indeed, data ethics makes it into CSTA's standards. Bullet points on the slide there for 11 to 14 and 14 to 16-year-olds of things that they should know about in terms of ethical use of data. So I come at this from a point of view of both cynicism, skepticism, and cynicism. Or is it the other way around? Skepticism, trust no one, and cynicism, question everything. So I think you want both of those principles involved in this. So look, ways of teaching that about data privacy, about the sensitivity of this personal information. We have written into our curriculum, children as young as 5 should be taught to keep their personal information private. What does that even mean? One of the things you tend to do in an introductory data science statistics course is get them to do a survey. It used to be on paper. These days we might use Google Forms for this, or Office Forms, is it? Or the equivalent version in Microsoft Office 365. So this is the sort of thing which your class could come up with, or which you might even do. We're really interested in making sure our school is safe from COVID. We're protecting the children in our school as best as we can. So we're going to do a survey about that. What's your email address? What's your name? What's your date of birth? I am immediately collecting personal information. I'm foul of COPPA in the States. I'm foul of the Data Protection Act in the UK. I'm foul of the GDPR in the European Union. So there are huge issues around collecting personal data in this sort of way. So take my survey. What's your gender? And we immediately go into this sort of binary distinction there. You have to choose one of those 2 boxes. It's a required question. Race, ethnicity, what's your height? What's your weight? There may be some pupils in your class who are not very comfortable entering their weight into this sort of form. This is personal data, isn't it? And then which of these symptoms have you had since January? Persistent cough, fever, loss of taste. This is now medical data. Have you been tested positive for coronavirus? So, do not do this, please. Do not fill in this form. Do not get pupils doing this sort of thing. If you want to collect data, then you've got to do it in an anonymous sort of way, because otherwise you're processing personal data. And this sort of thing, I feel, has no place in our data science classrooms. Work with the big data sets. Yes, it may be less engaging than doing a survey such as this, but there are good reasons why you don't want them. They should know to think twice before submitting this sort of personal information on any sort of form. Okay, so back in 1854, an epidemiologist called John Snow was interested in the cholera outbreak in London, particularly around Soho, and so started plotting on a map the houses in which people had died of cholera. And, this is the little black dots here are where people had died. And Snow's analysis said, look, these are all sort of clustered around one particular location here. And it turns out that here at the center of this is the pump. And of course, it was this pump that was distributing water that was infected with cholera. And so this is why everybody was dying. By doing this data collection, by doing this data analysis, Snow essentially cured or prevented this outbreak getting any further. So really good story in terms of the impact of data science before the computers. So you have this tension here. Is this personal data? That's personal data, definitely. Is this personal data? Well, is that personal data? I think it rather is. People have died in these houses. But on the other hand, by doing that analysis, Snow prevented more people from dying. So there's a real tension there. But making your students aware of this tension between their ability to give individual informed consent to data being collected and the wider public good. And this idea that epidemiologists have been the most successful bit of medicine by studying disease outbreaks, by studying how disease spreads. They've saved more people from illness, from death, than any other branch of medicine, so it is claimed. So collecting in the data could make a lot of sense. We have our phones with us. If you're using Apple Maps, there may still be people who use Apple Maps. Apple, during the pandemic, has been tracking how much people have been using routing directions. So how much they've been asking for driving directions, walking directions, public transport. Now, your individual start point, end point, that's very personal information. But in aggregate, you're seeing here on their visualization that, yes, from the beginning of lockdown in the United Kingdom, we really stopped asking for directions because we weren't allowed out of the house. During the November lockdown, people were still allowed out. During the most recent lockdown 3.0, it's dropped to a much lower level, particularly for public transport. Public transport never really picked back up, did it, to the baseline figure. And then we've got the other ones for driving and walking. Is that an appropriate use of my personal data when I'm asking for directions? It's aggregated. You can't find where I was on this, but you have that sort of aggregated thing across the whole of the United Kingdom. Google provide even more data or in aggregate for this. So this is looking at the whole of the United Kingdom about people's phone locations. This isn't just people asking for routing directions. This is where the phone was. They've got location services switched on. Google knows where they are. How's that for big data and tracking? So we see since the baseline, since end of January, February 2020, 61% drop in people visiting retail and recreation locations, and a 20% increase in people whose phones appear to be located at residential addresses. We day on day looking at, allowing for weekends are different from midweek. So is that okay? Is it okay for Google to collect that information together to provide that sort of analysis? You can get this down to sort of individual local authority level. So, they will provide you with the report on your particular local area. We have our Test and Trace app. We're not hearing very much about this, which connects to other Test and Trace apps. If you've got it on your phone, if the other person has got it on their phone, when the phones are closer than 2 meters from each other for a certain amount of time, a little signal is transmitted from one to the other, so they know that the phone owner has been in contact. So, it's a reasonably safe way of doing it. There are concerns about this. And choose to share the anonymous record on your phone. The data will be stored in a secure database in the UK, and that's meant to make me feel good about this. So, I think they're doing this in a reasonably robust and safe sort of way, but you get the message saying you've been in contact with somebody who has tested positive for COVID. You should now self-isolate. Singapore have a very similar thing. The original privacy statement on the Singapore version, Trace Together, said data will only be used for COVID-19 contact tracing, which is kind of the promise which my government has made about this particular app. Turns out, after questions in the Singaporean parliament, that okay, actually, if the police come with a request, they will release that data. The latest version of the privacy statement, we want to be transparent. Trace together data may be used in circumstances where citizen safety and security is or has been affected. The greater good? Changing trust? I don't know. I really don't know. So yeah, when children were allowed back into school here in England, then there was this notion of, okay, if there's an outbreak in the school, then we need to isolate the children who've been in contact with that particular individual. So then in the guidance from a Department of Education, where an outbreak in a school is confirmed, a mobile testing unit may be dispatched to test others who may have been in contact with the person. It's not clear whether that's going to be with their consent or not. I think it is with their consent. This is a medical procedure, but it's not clear in the guidance there. Now we have this sort of asymptomatic lateral flow testing happening in English schools, or happening in those English schools where young people are going. The guidance to schools says, this is really interesting drafting, I think. You will need to satisfy yourself that you have a lawful basis for processing the personal data. You might want to consider whether the duties prescribed in education legislation on schools to make arrangements to safeguard and promote the welfare of pupils provide sufficient legal basis without having to rely on consent. I think that's a really creepy statement somehow, that the greater good justifies not worrying about obtaining consent to the data being processed. They still need consent for the test to be conducted, to be fair, so it's not quite as bad as it sounds. So that's my trust no one bit. I think there's also developing this cynicism about the use of data and, this questioning how the data is being presented. So let me share with you a few of the sort of horrible infographics that's come up and the sorts of things that's happened, particularly with a UK focus, although I'm sure there are similar things over in the US. 2nd of May, we had this public target, that by the end of April, there would be 100,000 COVID tests being conducted every day. Very, very high stakes, government commitment to do this. A national achievement it's a national achievement achieved by a huge team of people. Matt Hancock and achieving 123,347 COVID tests on the last day of April. They met the target with 1 day spare, or on the last possible day. So how many people did they actually test, though? So yes, we did have 122,347 tests on the 30th of April. But somewhat disturbingly, they only actually tested 73,191 people. I think I'm more interested in the number of people they've tested rather than merely the number of tests that have been, in some sense, conducted. There seems a disconnect between those two numbers. Isn't that the one that we should have been focusing on rather than just the number of tests? And it turns out that we've been counting the number of tests that were posted out, the number of tests that were requested, when we come up to this magical number which meets the stated target. So there you go, 30th of April, we passed the 100,000 target, 122,000 tests. Depends what you mean by a test, of course, okay? Tests, so this tests include test processed through our labs and tests sent to individuals at home or to satellite testing stations. And then, of course, once the target's been met, pressure is off. We don't need to keep sending all of those out, so the numbers drop. That's the graph that they were presenting on the 9th of May. Okay, it's ramped up and COVID testing was happening. Now, if you go onto the testing dashboard, this is the sort of graph you see. Here's our 30th of April bar here, somewhere around 82,000 tests on the 30th of April, nowhere near the 100,000 that we were promised. To get to the 100,000 figure, you've got to go to sort of like 20th of May before we actually reach that. So they've rebalanced this. Oh, yes. Yes, Laurie, that's such a good one. Should have included that in the slide deck. Yeah, it turns out that Excel tops out at 65,000 rows, or the old version of Excel tops out at 65,000 rows. So we have no more than 65,000 test results. The spreadsheet clearly shows that. Okay, that's a really good example. And of course, your current, for a few more days, president in the US. I love this quote. This was when he was allowed onto Twitter. It's a while ago now. Cases are going up in the US because we are testing far more than any other country and ever expanding. Smaller testing, we would show fewer cases. There are two ways to keep the COVID numbers down. You could stop the transmission of the disease, or you could just test fewer people. Test fewer people, fewer people test positive. There you go. Solved. Okay. And this was classic visualization. So this is 5 counties with greatest number of COVID cases in Georgia. And wow, I say kudos, respect to Georgia here. That's a large number then. But look how well that drops over time to hardly anything by the end of the graph. Closer inspection suggests that the horizontal axis showing the passage of time is happening in an amusingly non-linear fashion over the course of late April and May. I don't think that's just a Georgian thing, but that's once you've got a time machine, you can get the graph to show whatever trend you want. Without the time machine, usually we think one day follows the next. Until the 9th of May, my government was very, very proud of the international comparisons. COVID came relatively late to the UK compared to some of our European neighbours. So we were showing this sort of graph. Okay, we're lagging behind France and Italy, but, broadly speaking, on the same trend line. After this point, they stopped showing this graph and, statisticians were saying, oh, international comparisons really don't make sense because countries count the number of cases and deaths in entirely different ways. I'm not sure that that's an entirely smart statement. You see what I mean about question these things? You should get your students to question these things. This is the UK figure. daily death numbers, and one pauses for a moment to just reflect on how appallingly high these numbers are. But then your eye is drawn to the sort of Manhattan-style skyline here of peaks and valleys here. So is this really saying that loads of people die on Tuesdays? How come COVID is killing people on Tuesdays each week? How come nobody dies Saturday and Sunday? Weekends seem to be a good time to have COVID because you're not likely to die. Well, it's because the date of the death being reported to the statistics agency. So of course, they've added in the smoothed out week on week average for that, the rolling average. But again, the deceptiveness of, oh, these figures are down from what they were yesterday. Well, that could be merely because we didn't actually report this. Prime Minister, the day that lockdown lifted slightly, we were allowed out. We could drive for exercise on the 13th of May. What I can tell the House, Parliament, Commons, is that we are getting those numbers down. The number of deaths is coming down. The number of hospital admissions is coming down. He does not mean that the number of deaths is coming down. The number of deaths was increasing day on day on day. The daily number of deaths may have been decreasing on the 13th. Oops, sorry, wrong slide. On the 13th of May. 13th of May, somewhere around here, isn't it? Okay, so the number of daily deaths is coming down, but the number of deaths continues to increase. People just add on to that number. So yeah, I don't think that's an entirely frank and honest statement. So yeah, there's two contrasting collections of data. Our Office of National Statistics do a survey of people who have got coronavirus. They pick a random sample from the population, send them a letter, make them do the test, process those test results, and this is a sampled approach to surveying who is infected with COVID. This kind of got the attention of social media in the run-up to Christmas, because what you're seeing here, the red line is secondary school students, the yellow line here is primary school students, and you see immediately huge increase in the number of secondary and primary age pupils who are infected with coronavirus in this sort of end of November after lockdown 2 into December. So this is, from the point of view of teachers, evidence that we really should be sending pupils home from school. This apparently new variant of coronavirus seems to be spreading amongst young people much more than had been the case hitherto. Could just be that they were mixing more, but no, there seems some evidence that this is young people being much more affected by this. The other version of this is people who actually go because they have symptoms, the symptomatic testing of COVID. I'm conscious that we are pretty much out of time now. Okay, so the positive test by age, you don't see that trend line. If you look at this graph, you see the yellow line, which again is my 5 to 9 year olds, primary school age pupils, is the lowest lot of the lot. So you have one set of people saying, no, primary school pupils not affected very much by this. Secondary school students pretty much in line with the population. Another set of data shows you an entirely different perspective on this. I am out of time. Thank you so much for listening to all of this. Let me see if I can easily get you to the final closing slide here. Can I move this along a bit? Okay, I think that's the last slide. We didn't miss very, very much out. But here's the link to the slide. Here's my email address. I don't blog very much at the moment, but I am on Twitter. Nora, that's very kind of you, Laurie. Thank you very much. I'm sorry, I should have allowed more time for questions and so on. I just talked at you. This is just such bad pedagogy. But thank you very much for sticking with me for this. Thanks, Christina. Praise of the praiseworthy, praise indeed. Oh, thank you, Diane. Hey, listen, there are other things happening. So, we're done, really. I will hang around in case anybody has questions in the chat. But there's like a closing keynote to get to, which will be much, much more interesting. Oh, bless you, BT. Okay, well, in the absence of any questions, I think I'm going to just leave this, but thank you for sticking with me. All right. Hope to see you all in person before very much longer. Really do. Bye for now.